The purpose of this video tutorial is to introduce the user to a new feature in Adapt Builder 2017. And this new feature is the ability to model steel fiber. Steel fibers that are now included in Adapt Builder 2017 are in the form of Bekaert Dramix 3D, 4D, and 5D fibers. These fibers can be introduced as a material property for elevated slabs, slab on piles, mat slabs, and slab on ground. In this example, we're going to focus on introducing steel fiber to a slab on grade. And in order to begin this process, we need to make sure we select the right options in the Adapt Builder splash screen. It's important to note that for fiber usage, the option that the user wants to select in order to do a mat slab or a slab on grade is Adapt Mat. Note that Adapt SOG is very specific to post-tension slabs on ground, and this particular option should not be selected when the user wishes to use fiber in any soil-supported slab. We're going to select the American unit system, and the design scope in this case is going to be reinforced concrete. We'll go ahead and select OK. The first step in this process is going to be to define a concrete material that includes fiber. So from the material menu, we're going to select concrete, and we're going to select the option to add Dramix FRC. This is the proprietary fiber that's a Bekaert product. You can see the Bekaert logo. If you click this logo, you'll actually go to a website which contains information related to this particular product. We'll go ahead and we'll say add Dramix FRC, and we could add multiple fiber types. We're going to just assign one fiber type to a slab panel. So this is going to be a slab on grade panel that would be part of a much larger slab, but we're going to individualize the panel, and we're going to consider loads on this panel and also the ability for those loads to transfer across joints using some joint transfer methodology that's been implemented into the program, and this is in conjunction with the ability to model the fiber. So we've assigned a new fiber. It's called concrete2_F, and this concrete fiber has just general concrete properties. For example, density of the concrete. We have a unit price, compressive strength in terms of the cylinder strength, F'(C), modulus, and so on. So these same generic material properties for the material still apply, but we have additional properties now that can be designated for the material. The first thing we want to do is we want to set up the design type for the material. So this is going to be a slab on ground, and this is important because it allows the program to filter the type of Dramix fiber that can be used for that design type, whether it be a strain softening fiber or a strain hardening fiber or both. So we'll go ahead and we'll select the option for slab on ground. And by doing that, the program will sort the types of fibers that apply to this particular design type. So if we go to fiber material type and we use the pull down menu, we can now see the list of fiber types that apply that are produced for this type of a design. And we'll go ahead and we'll select the Dramix 4D 65/60 BL fiber. And when we select the fiber type, we then get a sorted dosage range that we can apply. So in this case, the dosage range is 33 to 67 pounds per cubic yard. These are the dosages that can be applicable to this fiber type for this type of design. And you'll notice that the program reports some residual stress values, FR1 through FR4, which are used to generate a model for the tensile stresses for these particular fiber types. So, and these are the tensile stresses of the concrete at certain crack widths using the fiber type. If you want to override these values, you can select the option to override the residual values. The user can then come in here and modify these as needed. Now there are additional options or variables that have to be selected and defined. For example, we have a size factor that's applicable to some of the strength calculations that are made using this fiber type. So we have the size factor. We're going to auto calculate the size factor. We also have strength reduction factors, which are used for fiber specifically. So these are in combination with any reinforcement or post-tensioning that might be used for the system. And we'll leave those to the defaults shown here. Additionally, for a slab on ground with fiber, we can take advantage of the nonlinear response of the slab. So we're going to do that by selecting this option for nonlinear. We want to go ahead and set the type of environment the slab is going to be exposed to. Here for the relative humidity, we're going to consider dry air, and by changing this setting, we have different values here that are applied to that setting for shrinkage. Also, there's a relaxation and a friction coefficient that are required in order to determine some of the variables related to the nonlinear aspect of the design. So we'll leave these values as set, shown here. For additional information, we can reference the documentation related to fiber for Adapt Builder. Once the values have been set, we want to take note of this value FR1. This is 377 psi, and I'll go ahead and I'll say OK. And that's going to come into play when we want to use recommended spacing values for joints for a slab on ground with fiber. We'll go to the loading menu option, and from loading we'll select the option for Still FRC, and we're going to go to the Joint Spacing tab. So in order to size the slab that we want to model, the panel size, we're going to follow a few guidelines. For example, the recommended values based on this fiber type is a function of the FR1 value. Our FR1 value for the fiber that was selected was 377, and if we scroll down we can see that's roughly in between these two values here, which would put us at a spacing of about 60 feet, which is a slab thickness of 5.5. So we'll go ahead and we'll select our slab thickness. We'll say the slab will be 5.5 inches thick. We'll just follow this recommendation. It might be slightly smaller than that, might be 5. The material selection menu provides a material that we've assigned as a fiber material, which is concrete 2_F. And so we're going to just leave this alone for now. We're going to set the slab thickness. We show the material. We've basically come to this input screen just to look at these recommended values, and we're going to say, okay, we'll go ahead and size a panel that's somewhere in between 40 and 80 feet, let's say. So we'll say the panel is going to be 60 feet. We'll say okay, and we're going to model that panel. So using the modeling tools in the program, I'll go ahead and turn on this option for Snap to Grids, which is on the Snap toolbar, and I'll set the spacing here to 10 by 10 feet. And then from the Build pull-down menu, we're going to select Structural Components, Slab Region, and we're going to create a slab that is 60 feet by 60 feet. And remember, this is a panel of what would be probably a larger slab that might be an industrial slab on grade that is structural in nature. So we'll model that panel. I'm going to go ahead and double click on the panel to open the property menu, and we'll set the thickness to 5.5 inches, and I'm going to set the material to this concrete 2F. This is the fiber material, and it shows me right here what that material is. This is a slab on ground. The fiber type is shown as Dramix 4D 65, etc. The dosage is 33 pounds per cubic yard, and we're considering nonlinear analysis for the design of this slab panel. I'll select the green checkbox to close the panel, and now I'm going to save the model. So I'll go to File, and I'll select Save As. So once this file has been saved and the main outline of the slab has been modeled, we're going to now create a spring, a soil spring, which basically represents a soil support beneath the slab. So we'll go to Build. We're going to select Spring/Soil Support, and we're going to select Soil Support. And I'll just model this somewhere outside of the slab. It doesn't need to be modeled right on the slab as long as it engulfs the slab. So we'll double click on the soil spring. This is an area spring where we can enter the subgrade moduli for the soil, and we'll just leave this. We're going to leave this as is to 100 pounds per cubic inch. Notice this is a compression only spring, and I'll select the green checkbox to close that. I'm now going to go back to loading, still FRC. Under joint spacing, you can see based on the input that we've made, this chart below is really just a recommended value. So now we're going to actually calculate the maximum joint spacing for this slab thickness and this concrete type, and we'll select calculate. So the maximum joint spacing is 118 feet. We've modeled a slab of 60 feet, so we're within that maximum limit. We'll leave the slab as is, and you'll notice here under actual panel length, we want to go ahead and update that. I'll say 60 feet, and I'll say OK. We're now going to load the slab, so we want to make sure we have the loads on the slab that we want to perform an analysis for. So the first type of load that I'll model is going to be just a uniform live load. It just might be some load that we want to cover the slab with, just some baseline load for live load. We'll go ahead and select the slab, and if we go to loading load case library, we can see that there are actually two reserved load cases. There's a dead load and a live load. We could add additional load cases. For this example, we're going to leave these as they are. We're going to apply all of our loads based on one of these two loads. So the first load will be a live load. We just wanted to show that those are the two reserved load cases. We'll go back here to loading. Because I have a poly region or a slab region selected, we can go to loading, add load, patch load wizard, and I'll add a live load, let's say of 40 pounds per square foot or 0.04 kips per square foot. I'll create that live load, and you'll see we're looking at a top view now, but if I rotate this to a 3D view, we can see that load that's been applied to the structure. Now I'll go back to a top view. I'm going to change the spacing for my grids to 2 by 2. Actually, we'll use something a little bit larger than that. We'll do 5 by 5, and we're going to add now just a few point loads. So we'll go ahead and say loading, add load, point load. These will also be defined as live loads, and I'll go to the properties of the point load, and I'm just going to say that these loads will each be 10 kips, and we'll say this is a dead load. I'll select the green checkbox to accept that, and now we're going to just add a few loads. So I'll just add one load on each corner and one load really in the edge, and then I'll do a few in the interior. Okay, and those loads are then labeled sequentially 1, 2, 3, 4, etc. We're going to add a couple of line loads. We'll call these dead loads. So I'll go to loading, add load, line load. And actually, I assigned the point loads as dead loads rather than live loads. Let's go back and change these to live loads. So this is going to be set as 2 kips per foot. We'll add a load from this edge down to here, from this edge to here, and then we'll add a load just like so. And again, these are sequentially labeled 1, 2, 3. Now I want to turn the labels on because I need reference to the labels when I go ahead and I generate the load transfer factors. I'll save this. I'm going to turn off my my grid, and to manage the view of the loads with their labels, their magnitudes, I can select the blue eyeglasses. This is called Select Set View Items. And we're going to go ahead and turn on our load. I'll turn on the load IDs, let's say. We don't really care about the patch load. That's just one individual load. We know it's ID number 1, but these are the IDs for the point and line loads. And I'll turn off the patch load. We want to do that. We do not want to see the patch load. It's a little bit restrictive in what else we can view. So this becomes our model. Now we're going to go back to loading, still FRC. The next thing we want to do is we're going to go here to the load parameters. So we want to classify the type of load, and this is important so that we can determine a transfer factor for the loads in the proximity that they are included in, if it's a corner, edge, or an interior zone. So we're going to define a few of these loads as being, what classification they are. So we'll just do a couple of them as an example. So we'll say that load number 1, which is line load 1, it's a live load. We're going to call it a corner load. It's on the corner of the panel, and we do want this to transfer a portion of its load across this joint. So we're only designing this panel in particular, but a portion of that load, because there's a joint there, will be transferred to the adjacent panel. Now we just accidentally selected a line load. That's fine. We can relabel this. I'll call this an edge line load. I should have been down here at a point load, and we'll call that a corner load. And yes, we do want to transfer that. I'll also look at, let's say, number 2, which is an edge load. So we'll call this an edge load. Yes, we want to transfer a portion of that magnitude across the joint, and we would go through the loads and systematically determine which loads we want to consider as being transferred over the joint. So once we're done with that, we need to determine what the load regions are. So these load regions are used to classify the loads in their position and proximity to the edge of the slab, whether it's a corner zone, an edge zone, or a interior zone. And you can see this itemizes the slab regions. We have a slab region of 5.5 inches thick. Spring stiffness, the radius of elastic stiffness is shown here, and the edge is 3 times this value here, which is 80.56. The maximum interior angle is just the angle. It's a tolerance angle where the program will consider whether or not 2 sides of a slab become a corner zone. So we're going to increase this, let's say, to 120, and then the minimum slab edge related to corner zones we're going to say is, let's say, 12 inches. And this means that if there's a short jog in a slab, we're going to just say, well, any short edge of a slab jog would actually just be ignored, and we would still consider that whole area a corner zone. And then the next thing we're going to do is create load regions. Now once we create load regions, we can view them. So I'll go back to the top view. I'm going to go to the result display settings. It's signified here by the red eyeglasses. And I'll go down to the bottom here, and under Still FRC I want to turn on load regions. And you can see in this case the load regions are interior and edge. Green is edge, blue is interior. So there's some issue that we had with our input that did not create the corner zones. So we'll go back and we'll look at that. It's likely the angle that we entered. So if we go back to the loading Still FRC input, and under the maximum interior angle, just re-enter this value and select this value here to make sure that value is stored. I'll say OK, and prior to saying OK, we need to create the load regions again, then say OK, and then we can see we have corner, edge, and interior zones. So this indeed is a corner point load. This is an edge / interior line load. We're going to classify it as edge. The program can handle a line load that passes between 2 zones. This is an edge load number 2 that we classified. So we now have our zones considered, and the program, if we look at the load factors, I'll just zoom in here, you can see that the values for T corner, T edge, and so on are currently set to 0. So I'll go ahead and just increase the font size for those zones so we can see that a little more cleanly with the model viewed out or zoomed out. We'll go back to loading, Still FRC, under load parameters. Remember, we defined these as being near an edge of a crossing joint and classifying this as edge, corner, or interior. So one thing you may want to do is you may want to create the zones prior to classifying these. In this case, we knew that these were in the position that they were, so we classified them prior to generating the load regions. We'll go ahead and calculate the load factors. And you'll note when we do this, we have to have support lines input before we can generate the load factors for the model. We'll come back into the main model. I'm going to go back to the red eyeglasses, and I'll turn off these options here for the regions and the factors. I'm actually going to just default display the model and go back to just a single slab. And now I'm going to add support lines. So I'll turn my grids back on. My grids were at 5 feet, and I'm really just going to turn these 5-foot increments into uniform strips in either the X or the X and the Y directions. We'll go to strips, generate support lines or create support lines. I'll go to the input properties for the support line, and you can see this is set to X direction. So I'll go ahead and I'll just model these strips. Now, you're not required to model each and every one of them. I could take this and just replicate this down by selecting Modify, Copy, Move, All Transformations in Plane. This will be the negative Y direction, so we'll say negative 5 feet, and we're going to input an additional 12 copies of this. I'll delete the extra. I'll save that. I'm also going to do this in the Y direction. So I'll go back to strips, generate my support line. We want to cover this two-way slab in both directions with design strips. This is going to be Y direction. And I'll do the same thing. I'll start at one edge, and I'm just pressing enter to close that line when I snap on the second point. We'll modify again. This is in the X direction. We'll say 5, and in this case 11, and we'll copy that over. And now we have our support lines. Now the support lines are used to generate our design cuts, or excuse me, our design strips. Because we're working in RC only mode, the program has an option in criteria under the analysis and design options that will create column and middle strips. And this doesn't apply for a slab on ground. So we'll go ahead and select no to that. We want the program to generate a design tributary for each strip that's 5 feet wide, which means that this becomes a spline or a center line of that strip. I'll go to strips. I'll regenerate my design cuts. And by regenerating these design sections or design strips, we do two things. We generate a tributary, and we also generate a design cut that's perpendicular to the support line. So here we're looking at both of these as one, X and Y directions. If I go to the blue eyeglasses, under structural components, I'm going to turn off the X direction, and I'll look at only the Y direction, or only the X direction. I'll turn off the Y direction. So you can see I have just a handful of cuts in strip 1, strip 2, strip 3, strip 4, and so on. And the user can control the number of design cuts in each strip. So if I double click on this strip, and let's say I wanted to generate more design cuts under design section options, let's say I wanted to do 30 cuts for this one strip, I could update that and generate the strips again. And you'll notice here that if I turn back on the X direction, I have more design cuts along this strip. So you can refine the number of data points essentially for the strip. I'll go back and just reset that. Anytime you make a change to this, you have to generate the design sections again. I'm using the regenerate option, which just means that the program is calculating the design strips for us. We're not auto or self-defining them. So we now have our design cuts. Now I'm going to use a different option to turn those on. I'll go to the FEM View Design Results toolbar, and in the View Design Results toolbar I can see I have this display design sections, and this allows me to toggle between the two directions. Okay, so this is a prerequisite to designing or to determining the load factors for the design cuts. The load factors are what we assign and apply to the loads to in order to produce the nonlinear result for the slab. And so if we go back to our original intent, which was to generate those factors still FRC, we've input the load regions. This is auto written just based on the input of the slab. We set up our tolerances, we set up our load parameters, and then we also went through our joint spacing. And now we're going to create the load regions again just to go through the steps, and I'll calculate the load factors. And the program then uses the design cuts to generate the load factors applicable to this model. So we'll select OK. Using the red eyeglasses again, I'm going to turn back on our updated results. So we still have the same regions. We have corner, edge, and interior. Our load factors now are shown here for these particular regions. Okay, so the user can review the factors being applied for the transfer factor, and ultimately we want to get a design of any additional reinforcement in addition to the fiber for this slab. And so we'll go now to mesh the slab. I'm going to go ahead and analyze the slab, and I want to make sure I include the fiber load reduction. This is really including the nonlinear analysis aspect of this design. The program designs the flexural response of the slab for the nonlinearity. So anything involving shear, punching shear, or one-way shear, if that's applicable, would not be affected by the reduction due to the nonlinearity. So what we're doing is we're actually reducing the applied loads based on nonlinear factors for the slab. And by doing this, we have additional capacity based on the geometry of the slab and the dosage of the fiber that's been assigned. So we'll go ahead and we'll say OK. We're going to run the analysis for a couple of service and a couple of strength combinations. The service combinations also would not be affected. We're only looking at the strength combinations in this case. So for displacements, we're still looking at a linear elastic response. For strength, we're looking at the nonlinear response for purposes of flexural design. Once the analysis is done, for example, I can go to slab deformations under service total load, and this gives us those deflections based again on the elastic or linear elastic response. If I take this a step further and I design the design cuts, once I design these design cuts, this is where the program considers this effect of the nonlinearity, where we have additional capacity of the slab because we're going beyond the initial crack state of this slab, and we're relying on the fibers properties to provide that response for us. So we'll go ahead and we'll say OK. We want to save that. We can see if we look at the design results again, we'll look at the X direction, and I'll turn off the mesh here. I'll just go back, look at the X, and looking at this particular view, if I go to strength, dead and live, I'll go down here and turn on the moments for the design sections. These are the design moments for the strips in the X direction, and these design moments that you see, if you were to run the model without the nonlinearity option, these would be greater, just because again this is the way that the nonlinearity is realized. The program designs for these particular sections. So whatever the moment is, if this concrete slab with fiber capacity exceeds these moments, no additional rebar is required. For example, if I go ahead and let me just reduce the graph here, and we'll look at one of these moments here where it's kind of a peak moment, this 4.68 for example. If I double click on that section cut and I select design sections, in this case the program is adding a little bit of rebar for minimum requirements, for service total requirements, but this is not dictated by strength. The program has enough capacity based on just the fiber to meet the strength demand, but we are adding a little bit of rebar again for the purpose of serviceability. If we ran the slab without the surface reinforcement or the surface combinations, we would have no additional rebar needed for this case. And we'll go ahead and close that. And if we select FEM, generate the rebar drawing, under the enveloped condition, we can see additional bars that are required for this slab. Now, you can see there's quite a bit of reinforcement that's required, and one of the reasons that we're seeing this, so we'll go ahead and do that as an example. We'll go to FEM. I'm going to reanalyze the slab, and I'm just going to do this for strength dead and live and strength dead load only. I'll ignore the two minimum reinforcement cases. I'm still taking advantage of the nonlinearity here by this being selected, and we'll rerun the slab for this case. And looking at the bending actions, we need to go back to FEM and design the design cuts again. Okay, so that's done. We still have that moment of 4.68 shown, which is a strength dead and live moment. If I double click again on this cut, go to design sections, we can see no additional rebar is required. We still have capacity of 9.2 kip feet over this one cut, and the demand is 4 kip feet in this region at this design cut. So if we were to generate the rebar drawing now for just strength under the envelope, you can see no rebars required for strength. So this kind of gives an idea of the workflow for a slab panel using fiber in Adapt Builder. If you have any questions, please let us know. Our contact information is support@adaptsoft.com, or you can reach us at 650-306-2410. Thank you.